Hello, it's Keith here, and this is lesson 74 of the platform-specific series of my 650 assembly programming tutorials. Today we're looking at the Apple II. We've been recently using interrupts to time our music, keep it playing at a constant speed. We're going to try and do that on the Apple II today. However, to the best of my knowledge, we can't actually have a Vblank interrupt on the Apple II. So instead what we're going to do is we can detect it Vblank, but we can't interrupt on it. So what we're going to do is we're going to put a Vblank check during one of our primary loops, and we're going to catch the Vblank and we're going to update the music so we can play it at a constant speed. Now there is another challenge on the Apple II that we've already addressed before, which is it uses what I refer to as beeper sound, and this is where the processor itself has to generate the music by usually repeatedly flipping a bit, which builds the waveforms of the sounds. Now we did that work of creating the sounds within the Chibi Sound Pro tutorials, though that covered how the platform stuff worked, but it does cause us issues again today because a lot of our processing power is being used for the actual sound generation. So we're going to see all of that. Anyway, let's go over to our code and let's see what we've got today. Okay, so here is the code for today's example. And so we're basically we're not going to cover the graphics routines. Those were covered in the Mintile series, and there's a Max Tile series coming soon, which is better graphics. But what we're going to cover today is the new code relating to the music and the simulated interrupts. It's not really an interrupt at all, is it? Because we can't do interrupts actually. So what I've done is I've put this in the do strip routine. Now this routine is executed every time we are going to start drawing a strip of graphics to the screen. So whenever the sprite's being drawn in the background, this is constantly being executed. So we're going to use this to detect the Vblank. Now the way we detect Vblank is with a memory mapped hardware register port CO19. Now the top bit of this will define whether Vblank is on or off. Now if this is a 1, then Vblank is currently not occurring. Now we can actually use a branch if minus, because if the top bit is 1, then an 8-bit value would be minus, and so we can branch over our execution of the sound routine here if the Vblank is not set. If the top bit is 1, then it's effectively a minus value we're loading into the accumulator here. Now the slight catch is that apparently Apple decided to flip the way that this works. So if you're using the Apple IIc, the bit is actually the other way around, and so you would need to change this branch if minus to a branch if plus. I don't know why that changed, but it did, so that's just something to bear in mind. The example today, we're using a branch of minus. So anyway, that's how we are detecting our Vblank. Now, what we're going to do is then run this Vblank handler. This is usually the interrupt handler, but we've got no true interrupt this time, so I'm calling it the Vblank handler. So this is going to run the ChibiTracks play routine. ChibiTracks is my music software, multi-platform music software, and the play routine updates the sound. And in the case of the Apple II, as I say, it actually has to do some work to generate the sound. So assuming that there's not silence being played, it actually has to do some calculation work and change the waveform to generate some kind of sound. So that's what we're doing there. Now, in most cases, actually, this is taking quite a lot of processing power and is actually slowing down the drawing routines. But just on the off chance and for completeness, what I'm doing here is I'm checking to see if the Vblank has ended yet, and if it hasn't ended, we're waiting for it to end. So this is going to just repeat until the Vblank has ended, and the reason for that is, if you think about it, if we were doing a very small job in Vblank and Vblank wouldn't have completed before our job had completed, then we'd actually end up doing the job multiple times per Vblank if we didn't wait for the Vblank to end before returning. As I say, in the case of the music, in all likelihood, unless it's a silent iteration, this would not occur, but I think for completeness it's good to put that in there, so that's what I've done. You'll notice I've got this push pair and pull pair. These are macros. These push and pull 2 8-bit pairs that make up a 16-bit combination. HL is a 16-bit value, so it's D, B, C and IX. These don't have any particular meaning. They're just equivalents of Z80 registers. ChibiTracks was a Z80 piece of code, so I've matched the names there, but the purpose of them varies within the code. It's just important to have these 8-bit pairs that are combined into 4 16-bit values, and so I'm backing up and restoring them there. So that's all I'm doing to update my music accordingly. So let's just quickly discuss ChibiTracks and how it applies to this system. So we've got a song that we want to play. This is the binary file for song 1. This is the song that we're playing today. We've got a platform driver, Chibi Sound Pro. This is the platform-specific sound driver that deals with the particularities of this hardware. I've got a tutorial on that already, so please search Chibi Sound Pro and Apple II and you should find it. Then we've got the multi-platform code, the ChibiTracks music player, which is the same on all systems. It's the platform driver that abstracts the hardware and does that part for us. And then we've just got some common modules that ChibiSound and ChibiTracks that ChibiTracks needs more specifically to do the music. Now, ChibiTracks and ChibiSound do need a little bit of memory. So we are allocating 128 bytes of memory, and we've just got the address of ChibiSound around there. That's the memory. And we've got some pointers to some variables that ChibiTracks uses within that, and we're just initializing them there. We do have some options, some of which are specific to this system. Now, allow relocation, this is a ChibiTracks function, and this allows the binary file to be loaded to an alternate destination to the one that it was exported for. My music tracker, Windows-based .NET application, is called ChibiTracker Pro. This has an export option which allows you to select the end memory destination, and it's assumed that the file will be loaded into that address, but it might not be, because if you're working on multiple systems, different memory addresses do different things on different systems, and so it's often impossible to load to the same address on a lot of different systems. Allow relocation allows you to actually load it anywhere. It just slows down the loader and makes the player a little bit bigger. Allow speed change is similar. This allows the speed to be changed at playback time. For example, the song you heard today was designed for a 50 Hz system and had a play speed of 5, but we can change it to 6 to slow it down a little bit for a 60 Hz system, and it plays at roughly the correct speed. This also slows down the play, makes the play a little bit bigger, but it allows some flexibility at playback time. If you don't want this flexibility, run this line out and enable pre-multiply speed on the export within the ChibiTracker Windows software, and that will make your player a little bit smaller, but it will make it impossible for you to change the speed at playback time because it will have already been multiplied into the binary file. Now, there's a few special options for the Apple II. Fast Silent is one that's useful for today. Now, the general ChibiSound Pro driver for the Apple II assumes that you're just going to be playing the music in an infinite loop with nothing really going on in between, maybe like a press fire to start game loop on a title screen, something like that. And in that case, if there's nothing being played by the music file, there needs to be a pause of roughly the same length as when there is sound played. As I say, the processor's doing the job of generating the music. If we didn't delay when we were doing nothing, the pauses would effectively disappear. However, if we're timed via interrupt or by our fake interrupt today by the Vblank, we don't want to delay when there's nothing to play, because we'll just be wasting CPU power and we could be drawing when that CPU was doing nothing. So this fast silent option enabled will not wait when there's nothing to play, and that is correct for today's example. Single channel doesn't work well with this music. That will basically only play the first channel and it will ignore the second and third. ChibiTracks supports 3 channels, but the first is the most important. However, this music file I was playing today was ported from another version that I made with Arcos Tracker. So the main theme of the music isn't in channel 1, so it doesn't work very well with this option. But that is an option you can enable, and then you'll ignore channels 2 and 3. If you disable that option, it will play the first channel that actually has something playing on it. So if 1 is playing nothing, it will move to 2 and move to 3. It actually plays the loudest, so if channel 1 is really quiet but channel 3 is really loud and channel 2 is doing nothing, it'll be channel 3 that ends up being played by the hardware, because our hardware today can only do 1 channel. Finally, SMS transpose. This is for systems that can't do low notes very well. It will basically move all the notes up 1 octave. The pitches are wrong in general because they've all moved up 1 octave, but the low notes will be correct because this system and a few others can't do very good representations of low notes. So it's a trade-off. It depends whether you want the tones to be correct or you want the low notes to be roughly accurately represented. So I've enabled it today. Now, when you want to actually play music, it's very straightforward. First, you need to initialize the platform driver. You run ChibiSound Pro in it. You only need to do that once. You then need to load the address of the song into the song base. So we've done that there. Start song will actually load in the variables of the song and start playing. And then we have a specific option just for today's system. Now, today's system, it's actually, as I say, the process is having to do the sound generation work. And so the amount of time it spends each tick playing the sound, the longer we spend, the better the notes will be, but the slower the gameplay will be. And so it's a trade-off, and the higher the number, the better the sound, the smaller the number, the worse the sound, but the faster the game. So I've selected 4. That's about the minimum I think you can use. You can select one, that will work just fine. It will run, however, the problem is that the sound will be so poor that you might not be able to tell what's playing. So basically we're spending so little time generating the music there that it just sounds like a bunch of clicks, whereas if we change this to 16 and we run again, well, now we will have very clear tones, but the game will be extremely slow indeed. I think we're actually spending more than one full frame generating the sound there, and so the song is actually playing too slow because we're missing an entire frame's Vblank because the length of the note generation is too long there. So, as I say, this system has a very basic sound driver. In my experience of the ZX Spectrum's beeper system, which was very similar, I don't think really any games tried to play music during gameplay. Like the example I'm showing today, they only really did it on title screens where there was nothing going on except for music generation. But you know, for completeness, I wanted to show that it was, at least in theory, possible, if not necessarily practical. So here's the example. And as I say, in a more sort of relevant case, it's a good example of how you can detect Vblank, because if you're going to write games that you want the timing to run consistently, no matter how slow the game action is going on, you know, maybe you've got sort of a game tick that's controlling the action, well, you need to be able to detect something like Vblank and control your game movement according to it, so that, as I say, whether there's one object on screen or 100, your game logic is executing at a constant speed. And today's example at least showed that's possible, even if, as I say, to my knowledge, you can't actually use the interrupt. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.